let's dive into 5 examples which relate back pressure and density. Okay, so here's the first one. So based on this figure below, okay, so we want to be able to find what the pressure is. So that's our goal. Notice that they give us an angle there as well. So we're going to tackle these kind of one by one. So for part A, so it says the area is just 2 meters squared. So we have that. And then we have the actual force, okay? And then the force is 15 newtons. Notice the angle is 0. Okay, so this is the force, okay, which is 15 newtons at an angle of 0. Now, if you think back of pressure, so pressure is the force, but it is the component of the force which is in the normal direction, right? So it is normal, basically perpendicular to the actual surface. And this is divided by the actual surface area, okay, that it has. So now, if the angle is 0, like it is in the first case, then this is very simple. Okay, this is just going to be 50 newtons divided by the 2 meters squared, and that is going to give us the result in SI units of pascals, which is Newton per meter squared. All right, so we can just dive into that, and that's going to be, I guess, 7.5 pascals. All right, so that's what you would get in here, and that's the 2 significant figures that we have. That's for part A. All right, let's dive into part B. So in part B, so we do have a change. So notice it's the same force, but now the angle has changed. Okay, so it is 30 degrees. So this is, worth kind of drawing for yourself. So if you have, okay, so here's kind of the normal to the surface. Okay, so if this is the surface right here, so this one right here, you have, this is the normal component, right? So this is what we want. But it is telling us that the force, now it actually doesn't matter if it's kind of on the vertical side on the left or on the right. Okay, so if the force, okay, is at an angle of 30 degrees, right? So now you have to kind of use trigonometry to be able to find. So if this is 15 newtons, we can't just do the same thing we did above, because it's not the entire 15 newtons that is going to be causing the pressure on the normal side. So we have to find actually this component, okay, right here, all right? Knowing that the angle here is 30 degrees. So if you kind of recall with your trigonometry, so if you want to find that component, so what you're going to have is, I'm going to just take, because it's the adjacent, so I'm going to use cos. Okay, so if you do this, so it's going to be cos of the angle, okay, that we have, which is cos of 30, which is just equal to the adjacent over hypotenuse, right? So that's what we have. Now my adjacent, okay, so to this angle, well, this is the adjacent right here, and then this is the hypotenuse. So really the hypotenuse is the 15 newtons. So if you bring that over on the other side, so again, this shouldn't surprise you that the actual component, I'll just put n in terms of the normal component of that force, is going to be 15 cos 30, right? So this is what you would have in there. And so 15 cos 30, well, cos of 30 that you have is actually 3 over the square root of 2, but you can utilize your calculator as needed. So 15 times, and this is going to be cos of 30 degrees, and this gives us so basically almost, okay, so you're going to see there, so 12, 9, 9, etc. So almost 13 newtons. And now, indeed, so once we have the force, we can, take this force and then divide it by the area, which is still 2. So in this particular example, the pressure would have been, so this is just the 2 significant figures, which would have been 6.5 pascals, which is, notice, lower, okay, than the previous one, because you are at an angle. All right, so that would have been the second example. Now the third example right here, okay, so that we have, the area has changed. So the area is 5.2 meters, okay, squared in there. And then the force is 2.5 kilonewtons, okay, so we're gonna have to be careful a little bit. I'm gonna actually remove this out of the way in here for myself so that I can rewrite these in. So my area is 5.2. All right, so that's still in metric standard units. The force, so it's kilos, okay, so or kilonewtons. So I'm going to just change it back to newtons right there. And then I have an angle of 45 degrees. So this is going to be exactly the same thing, right? So you have your angle. You want to be able to project it back on, okay, so that particular angle that we have, and try to see what that actual force would be, all right? So in terms of the normal component. So if I do that, I'll do the same thing as I did before. So 2500 multiplied by cos of 45 degrees, okay, which is 1 over the square root of 2. But again, you can use your calculator in there. So this is what we have. So my pressure, okay, so within here, what I would have is, okay, so let me remove all of this. Then the pressure, so that's 1767 point, etc. And then this one is just 5.2. So this is super easy, okay, to be able to plug this in. And now the pressure is definitely, much higher. So for this example, would have been, 339. Oh, I guess it's 340. Okay, so I'm going to round it back in. This is to two significant figures, so it's going to be 340 right there. And that's going to be pascals. Okay, so much higher, but that's because of the kilonewtons. So that's how you would approach these. So the main idea for you to remember is when you are dealing with pressure, it is the normal component of the force, which is basically perpendicular to the surface area that we take, and not just any force, okay, at any angle. So this is question number 1. Okay, so that's all that we would have here. Here's the second example. So now this one is just based on conversions and units. So pressure has a lot of units that you're going to be running into. So, you can see here, so there's units that you have. So there's ATM, which just means atmospheric pressure unit. That is equal to quite a lot of pascals. Okay, so it's 101, 325 pascals, or approximately 101 kilopascals. And that is equal to 14.696 psi. Okay, and that's pounds per square inch. Okay, so if you're using pounds in terms of your force, and then inches squared in terms of your area, so that's just psi, and then that equals to 760 millimeters of mercury, which is very commonly utilized when you're measuring, for example, blood pressures. All right, so these are kind of 4 different units that we carry. So let's take a look and see how we can knock off these conversions. So the first conversion, okay, so which is 36 psi, it asks us to change this back to pascals. All right, so in this case, we can do our old school. So psi, we want to cancel that. That's going to be 14,696. And then on top, well, we have exactly, okay, what this would be, which is 101,325 pascals. So the psi's will cancel, okay, and then we have our result. All right, so if you look at this, so 36 multiplied by 101,325, and then divided by, this is going to be 14.696. All right, so it's going to be quite a big number. So 248210. Actually, let's check. Okay, we started with 2 significant figures. So this would have been 250000. Let's see this. 250. Yeah, okay, and 3 zeros. And this would have been pascals. All right. That's the first conversion. The second conversion that we have, which is 87 millimeters of mercury, we want to change it to atmospheric pressure. So again, so we have all of this given to us. So this is, it makes our life a lot simpler. So that's 1 ATM. Okay, so this one is 87 divided by 760. And 87, so that's 2 significant figures, so I'll just leave it in 2. So 0.11 atmospheric pressure. All right, so that would have been the second one in here. And then for the third one, we have 520 pascals, and we want to change this to millimeters of mercury. So, okay, so we gotta go back in. Okay, so pascals is going to go in the denominator, and we have millimeters of mercury in the numerator. All right, so that's what we have there. So 5200 times 760 and divided by 101,325. Okay, so and this is 39 millimeters of mercury, okay, to two significant figures. So those are the three examples. So these are, handy to have, if you're utilizing this, try to write it down for yourself somewhere. Okay, so they'll help you out. All right, so that's it for this one. In this example, we have given blood density, which is 1.03 grams per centimeters cubed. The blood is inside a container with dimensions of 15, 18 by 12. Okay, so it's a rectangular prism. And now we want to calculate what the weight of the blood inside the container is. Okay, so neglect the weight of the container. All right, so it's just the blood itself. Okay, so now this is going to force us in to try to understand kind of how to set this thing up. So if we have, within here, okay, so we kind of are looking at something like this. We have a, okay, so this kind of goes up in this way. So it says it's 15, 18 by 12. So within here, so it doesn't matter what you label as what, because the volume itself, now I'm going to keep it in metric standard units, because if I want to know what the weight is in here, right, so I want to be able to just use the metric standards. All right, so we have volume, so that's going to be 0.15, okay, meters times 0.18 meters times 0.12 meters. All right, so that is my volume in general. Okay, so this is going to be 0.15. The order won't matter because it's multiplication. So we have 0.00324. This is meters cubed. And now they give us the density. So the density is, so notice that they give us 1.03 grams per centimeters cubed. Now recall that when you're given density in grams per centimeters cubed, in order to change it to metric standard, you don't actually have to do any major conversions. So in order to do that, all you have to do is, you multiply this by 1,000. So this was kind of pointed out, okay, in one of the questions I've actually done before. Maybe I'll put up a link up above there to that video, okay, if you want to check it out. So within here, so this just means 0.30, and this is going to be now kilograms per meter cubed, right? So that's just that multiplication by 1,000. Now, if I have this, density in general is equal to my mass divided by volume. So if I know the density and I know the volume, then my mass is equal to density times volume, right? So once I have this, which is just 1.030 multiplied by the 0.00324, so that gives me what the mass is. All right, so I already have this on the calculator, so times 1.030. So that gives me 3.3372. This is kilograms. Now, if you want the weight, okay, so within here, so if you're interested in the weight, well, weight is just mass times gravity. So if you take your mass and you multiply it by gravity, you're going to get what the weight is. And this is going to be 32.7. Now let's see, I think it was two significant figures. Okay, the lowest amount. So it's going to be 33 newtons as your weight. All right, so that's how you would actually approach this particular example. So get the volume, you have the density. If you multiply the two, you get the mass, and then from the mass you can find what the weight is by just multiplying by 9.8. Now calculate the pressure at the bottom of the container. Okay, so the bottom of the container, let's say, was 15 centimeters by 18 centimeters. So in this case, if they want to be able to find out what the pressure is in part B, well, please remember that pressure is the normal force, right, that you have divided by the area. Now the weight, obviously, okay, that is pushing down. So the weight of the blood itself, it's basically all carried on that bottom, right? So it's basically just pushing the entire thing. So it is, you know, the normal. And we've just found what that was, all right? So this is, you know, 32.70, etc. So if we know what that force is, so that is the weight, the area now, so now the area itself is 0.15 times 0.18, okay? And that's going to give us what the answer is. So since I have this on the calculator, I'll keep it divided by, and then I'll put in brackets here, 0.15 multiplied by 0.18, okay, equals, notice there's quite a bit of pressure there, 1, 2, I guess again, you know, 2 significant figures, so that would have been about 1200 pascals, okay, or 1.2 kilopascals that you have. Okay, so here I'm going to actually write it down because I'm aware of the next example. Okay, so it is approximately, okay, this much. Okay, so I'll just keep it in there. But that is it, okay, for those two components. Now, this example, which is related back to the previous one, says calculate the pressure at the bottom of the container from the previous example using the pressure at a depth formula. So indeed, we can always find what the pressure is by just using this formula. It's a very simple formula to use. So pressure is just equal to the density times gravity times whatever height, okay, we might be dealing with. So now notice the density was 1030, okay, so kilograms per meter cubed. Gravity is 9.8, and then the height, okay, so if you go back in here, since they said 15 and 18, so the height was 12 centimeters, which is 0.12. So if you take this, now I want to, so this was what we got. And now if I multiply, there you go. So it's exactly the same. And again, I mean, you can round to 2 significant figures if that's what they ask you or whatever it might be, but notice that it's exactly the same what we got. So we did quite a bit of work. We found the entire weight of the fluid, in this case the blood, and then, you know, we have to find what the surface area is that it's pressing down on, and we got 12, 11, 28 just by the definition of pressure, which is, you know, the normal force and then divided by the area. But you can just use this, and this is the power of finding pressure at a depth. It's just so much simpler. Just if you know the density, just figure out what the height is, and, you know, there you have it. So that's this example. Here's the last example, at least for this video, so that we have. So it says, what pressure would an object feel if submerged 150 feet in water? Assume 1 meter is 3.28 feet. Okay, so again, this is nothing but pressure at a depth. So pressure is equal to the density multiplied by the gravity times whatever height or depth, okay, that we have. So within here, so water, okay, is 1 gram per centimeters cubed, which is the same thing as 1,000 kilograms per meter cubed. Okay, that's just, okay, density. So you can go back and forth between them by multiplying by 1,000 if you're going from grams per centimeters cubed to the metric standard. So now this is 1,000. G is 9.8, and then the depth is 150 feet. Now I have to be careful. I have to change the feet back into meters just to make it metric standard. So this is going to be 3.28 feet. This is 1 meter equals, so 150 divided by 3.28, that's 45.73, etc. Now I have this on the calculator, so I can, you know, punch this in, okay, and find out what that pressure is. So my answer times 9.8 times 1,000, and I get 44817, you know, 07, etc. Okay, if you round this off, how many significant figures? 2, I guess, again. So this is going to be about 450. Okay, so it's quite a lot of pressure, okay, that we would feel about 150 feet down. And that's why you typically have to get acclimated, okay, within and you know, going down okay, that deeply, you'll see what the pressure change, okay, will be. This is of course the pressure change with respect to the atmospheric pressure. It's kind of the gauge pressure that we have. So it's a lot, right, of pressure. All right, so that is it for this particular video. Thanks for watching. Hope that you found this useful. Bye everybody.